Well, everybody, welcome to our e-learning day extravaganza. Today, we're going to combine some of the stuff we talked about before. We've talked about homomorphisms. We've talked about subgroups of groups. And what we're going to do is we're going to do section 3.2. Classification of cyclic groups. So what do I mean by classification? Well, what I mean is the following. I'm going to give you a theorem that says if you have a cyclic group, then I can tell you exactly what it looks like. It must be in this family of groups. So if you tell me group cyclic, I'm going to be able to tell you more or less with very little knowledge, with no knowledge of what the order of it is, what the group is isomorphic to. So, without further ado, I should tell you, in fact, what it means for a group to be cyclic. A cyclic group is, well, let me give you that definition. A group G is cyclic if G is generated by X or some X in G. So I can find an element of the group such that every element in the group is a word made out of X and X inverse. But of course, words made out of a single letter are much easier. So if a group is cyclic, and we say in this case it's generated by X, then G is just all powers of X that you can muster, all integer powers of X. And of course, X is 0, power 1 is the identity. It's easy to see that this is a group because if the product of X to the A and X to the B is X to the A plus B, and if A and B are integers, so is A plus B. So the product of two any elements of this cyclic group are still in there. The identity is X to the 0. That's what leaves everything alone. It's associative because addition of the integers is associative. That's easy to check. And everything has its inverse. The inverse of X is X inverse, X squared, X minus 2, and so forth and so on. Right? By the way, let me point out that this group here is this is an infinite list, but this could be a finite set. For example, here's a little group here. I've got just the powers of X, and I'm declaring that X to the fourth is 1. So this is just kind of like a clock, right? X times X squared is X cubed. X times X cubed is X to the fourth, which is 1. X squared times X cubed is X to the fifth, which is back to X, and so forth. Notice that if I make that list like I did over here, this translates to X to the minus 1 is X cubed, that's the inverse of X. This is 1, X squared, X cubed, and then it begins to repeat. So, like I said, nobody said that everything in that list had to be different, but this is what the definition of a cyclic group is. What examples have we seen of cyclic groups? Well, we've seen a large class of them. Now, I wrote this is a good exercise. I think I wrote the group here, written multiplicatively. But here's some examples. Uh, uh, the ordinary integers is generated by 1. Now, remember, careful, this is under addition. So instead of the powers of 1, I mean adding 1 to itself that many times. So here the elements are 1, 2, 3, 4, forever. This is C. It's cyclic. It's generated by 1. All right, so everything in there can be obtained by combining 1 with itself enough times, and maybe its inverse. Here's another example. We've looked at several examples. This is under addition. C mod n under addition, 0 bar, 1 bar, 2 bar, all the way to n minus 1 bar. You add like a clock. This is generated by 1 bar. And actually, this may have more generators, but 1 bar certainly works here additively. Let me give you a spoiler. I'm going to spoil a little bit for you here. Every cyclic group is one of these, is either the integers if it's infinite, or Zn if it's got finite order. That's where we're going with this classification. So if I walk up to you on the street and give you a cyclic group, all you have to do is ask me, what's the order? If I say it's an infinite cyclic group, it's isomorphic to this. If I say it's a finite cyclic group of order n, it's isomorphic to that. And so we're going to get to see why that's true. Let me start off with the following result, following proposition here. Proposition 323, I guess. If G is cyclic and generated by X, then the number of elements in the group G is equal to the order of X. This has come full circle, I think, with our definition. Remember how I pointed out earlier, it's like, what's this all about? The order of G is just the number of elements in the group. The order of X is the smallest positive integer, such that you can take that power and combine it with that self that many times you get the identity. This is the connection. Right, so let's prove this. The order of X is the smallest n such that X to the n is equal to 1. And so for infinity, if no such n exists, so let me point out that suppose first that the order of X is infinite. Then equals 2, x minus 1. And notice there's no repetition. If the order of x is infinite, then all powers of x are distinct. Because, let me point this out, if x to the a is equal to x to the b, with a less than b, then x to the b minus a is equal to the identity, which is a contradiction because the order of x is infinite. So what have we shown? Well, we've shown, so if the order of x is infinite, then the order of b is infinite. So that takes care of this in the case that the order of x is infinite. Now, on the other hand, what if the order of x is finite? Now suppose and I want to let 1, 2, 3. So let's let I be just a set of the first k integers, where k is the order of this, and consider the function f from I into g. And how am I going to work this? F of m equals x to the m. Right? So just whatever integer I see, I take x to the m power. So let me point out f is a bijection. Let me be careful here. This is not a homomorphism because this is just a collection of integers. It's not a group. But I claim that as a set, this is a bijection. Suppose first that f of m1 equals f of m2, and here we'll assume that m1 is less than or equal to m2. Then this means that x to the m1 is equal to x to the m2, which implies x to the m2 minus m1 is equal to the identity. But m1, I'm sorry, m2 minus m1 is between 1 and I guess the biggest, and it's less than or equal, I guess k minus 1. So in particular, this is a positive power of x that equals 1. But, and this is a contradiction. Why is this a contradiction? Because k is smallest positive power. Such that x to k is equal to 1. So it can't be m2 minus m1. I meant to say this should be, actually, I forgot that I put less than or equal to. My apologies. This should be 0. K, but I'm still okay because K is the smallest positive, such this is true. So this implies K is the smallest positive power. This implies that M2 minus M1 is equal to 0, which implies M2 equals M1. So F is 1 to 1. And finally, it's fairly easy to see that F is onto because if we let x to the j be in G, I claim that we're covered by this, right? And here's the proof. This actually might help you on some of your homework. Actually, notice that x, we're going to use Euclidean algorithm to write J is QK plus R. Where R is between 0 and K. Remember, we divided J by K, and we got this remainder here. Notice that x to the J, or I'm sorry, x to the R is x to the J minus QK, which equals x to the J, x to the K to the minus Q power. This is the identity. And so x to the R equals x to J, where so in other words, what we've shown is an arbitrary element of G, which is a power of x, can be expressed as a power that is between 0 and K. So f of R equals x to the R, x to the J, and so F is on here. So in other words, here's the big takeaway from this. The order of an element is the order of the subgroup that it generates, right? So the order of the element X is the order of the little group that it generates inside there. Let me give you another proposition that you will see is kind of neat. And again, depends on the properties of integers. Let's say that X is an element of the group G. X is just any element of G. It doesn't even have to be a separate group. And M, N, and the integers are such that X to the M, and let's just say integers minus 0, so I don't want to mess with anything. So suppose that X to the M is equal 1 and X to the N is equal 1, then X to the D equals 1, where D is equal to the GCD of M and N. So if X to the N is 1, X to the M is 1, then X to their greatest common divisor power is 1. Here's the proof. There exists A and B in the integers, such that AM plus BN is equal to 1. Or I'm sorry, equal to D. There we go, the greatest common divisors. So X to the D is X to the AM plus BN, X to the N to the A times X to the N to the B, which is 1. And there you go. X to the greatest common divisor power does exactly what you want it to do. Okay. Let me give you, I'm gonna word this a little bit differently than what I did in the notes. I'm gonna go ahead and give you the big theorem here. Theorem. That G be a cyclic group generated by X. Then G is isomorphic to Z if the order of G is infinite and G is isomorphic to Zn if so this puts the family of cyclic groups into two nice little neat packages. Number one, the infinite ones, all of them isomorphic to Z. I don't care any cyclic group that's infinite is isomorphic to Z. And if it's not infinite, then it's got a finite order n, it's isomorphic to Zn. So there's a cyclic group for every n. And okay, so let's try this. Suppose suppose G is infinite. G is, of course, the set of X n is Z. And I'm going to define phi from Z and G by phi of n is X to the n. This is my homomorphism, and I'm going to show that it is a homomorphism and an isomorphism. Well, notice the phi of n plus m is X to the n plus m, which is X to the n, X to the m, which is phi of n, phi of m. So it respects the operation going from addition to multiplication. Okay, so it's good, all-American homomorphism. What about the one-to-one and onto? Okay, here's something from last class. It suffices to show that the kernel of phi is equal to only 0. This was one of our results from last time. A homomorphism has to be a homomorphism is one-to-one if and only if its kernel is trivial. Consists only of the identity, which is ES0. Okay, well, certainly 0 is contained in the kernel. So suppose n is in the kernel of phi. Now let's see, what does this mean? This means phi of n equals X to the n should be 1, which is the identity in the group written multiplicatively. But since G is infinite and G is generated by X, then the order of G equals the order of X. And this implies, since Xn equals 1, n can't be positive because the order of X has to be infinite, n equals 0. So the kernel of phi is 0 and phi is 1. Okay, how about onto? That's clearer in a certain sense. It's onto any element of G is of form X to the m for some m and z. Notice that phi of m equals X to the m. And so an arbitrary element is in the image. So phi is an isomorphism. And G is isomorphic to Z. There we go. that takes care of the infinite case. What about the finite case? Well, the finite case, I'll do this argument quickly because it's a kind of a repetition of some of the stuff we've done. Now suppose that we're n. I'm going to do the same thing I did before, except this time I'm going to do in this case, let me point out that, of course, I can list the elements G. These are the distinct elements of G, and they cycle back. Another power of X gives you X to the N, which is 1. I'm going to define B from Zn to G this way. I'm going to put the hat on this. I'm going to write my elements with my hat on it, Zn, to distinguish them from ordinary integers. This is equal to X to the K with the hat off. This is an integer. Now, be careful, folks, because the first thing I have to worry about here is I have to worry about whether this is a well-defined operation, right? Because there's many ways to write this particular representative, right? So, for example, if you're in Z mod 2, you could write this as 1 bar or 3 bar or 5 bar. They're all the same. And I got to make sure that I get the same answer no matter what I do. So how do I go about this? Well, suppose K1 bar equals K2 bar in Zn. This means that K1 minus K2 is a multiple. Yeah. Right. Well, so what does this mean? This means that K1 minus K2 is Mn. So it's just some integer multiple of n. So if you look at phi of K1 bar, this is X to the K1 by my rule here, which is X to the K2 plus Mn, which is X to the K2, X to the N to the M. But notice in this group, G is cyclic border N, X to the N is 1. So this thing right here is just the identity of the M that vanishes. So this is equal to X to the K2, which is phi of K2 bar. So it doesn't matter which representative you pick for the bar thing, you get the same answer. From here, it's fairly easy to show. Modular arithmetic allows me to write this way. X to the K1 plus K2. We know this is well defined now. And this is X to K1, X to K2, which is phi of K1 bar times phi of K2 bar. So it's a homomorphism. Notice this is onto. Because in X to the K is phi of K bar. So you give me an X to K, I'll give you the K bar, and it goes there. So since the cardinality of Zn and G are the same, they're both of size n, and it's finite, this is important. Phi is also 1 to 1. Because if you have an onto function from a set of a finite n to another same size n, if it's onto, it also has to be 1 to 1. So this is also an isomorphism. Okay. Let me give you the following kind of neat computational results here. And I think I'm going to defer maybe for this a little bit. This is more business properties of the integers here. Proposition, theorem 326, that is. Let G be a group and X in G of order n right. Number one, if n is infinity, I hesitate using that notation, but hopefully it's so. In other words, what I mean by that is if X has infinite order, then the order of X to A is infinite as well. So if the order of X is infinite, the order of X to A is infinite for all non-zero A. Of course, if it's zero power, then X to A is the identity. That's finite order. Number two, if n is less than infinity, so if it's a finite number, then the order of X to the A is n over the GCD of A and n. Okay. So this one right here, let me just kind of sketch this out here. For this one here, if order of X is infinite, and suppose that XA, or let's say is M, well, doesn't this mean that X to the A to the M is 1? Because this to the n power has to be 1, which implies order of X is less than or equal to AM, which is a contradiction. This establishes the first statement. As long as A is not 0, then this holds. And the second statement, for the second statement, let me first notice that if you look at X to the A, to the N over D, here, let me write this way. D is GCD AN. If I just write that here, I will save a little time. And I'm also going to use the notation A equal A prime D. I'm going to need that later. So D is the greatest common divisor of AN, and I'm going to pull that D out of A, leaving A prime. Well, if we look at X to the A, to the N over D power, this is equal to x to the n, the a over b power, just swapping out that a and n there. And of course, v divides a as well, so this is a good bona fide integer, which is 1 to the a over d, which is 1. So in other words, what that means is that the order of x to the a divides n over d. The order of x to the a divides n over d. Because n over d to this power gives you, or x to the a to this power gives you the identity. So that means that the order must divide. That's a homework problem, actually. Now we need to show it's the whole shebang. So let's suppose that x to the ad equals 1. Actually, let's do it this way. Now suppose that x to the ax equals 1. Well, this means that ax must be a multiple of n. And so a and z. Ax has to be a multiple of n. And I am going to revamp this using this little equation here. So a is a prime dx equals kn. Now notice that this is kind of a groovy little thing. Notice that a prime divides kn, and GCD of a prime and n is equal to 1. So from our first homework, we know that a prime divides k. So I'm going to use this to write k equals a prime, k prime. And do perhaps some further substitution. So now I get n k prime. Well, so let's do this again. Going back to this equation here, I've now got this is a prime k prime, and I can kill that a prime, and I get dx is equal to k prime. Okay. And hence, n over right. So and so now what we get out here is so what do we get here? What we're trying to do is show that well, so notice that let me get this square right here. Nk prime is right. So what we have is nk prime, which we had here, is I must have got this equation right here. This is, let's try this again. A prime dx is kn, which is a prime k prime n. There we go. Copied that wrong. So k equals a prime k prime n, and so now what we get is So I want n over d to divide x, and I guess that's what I get. Let's see, so canceling the a's here, dx equals k prime n. And so what does this mean? N over d times k prime. Remember, n over d is an integer because d was the greatest common divisor of a and n. So what this says is, so n over d divides x. And so this establishes what we got. The order of xa is n over d. Okay. So moving forward, let me give you, and this next theorem is talks about generators. I will leave some of this as an exercise. Theorem 327. Suppose that H is cyclic, that is, it's generated by some X. If the order of X is infinite, then H is generated by XA if and only if A equals plus or minus 1. If A is not plus or minus 1, then XCA generates a cyclic subgroup of H. It's actually still infinite, but it's a proper subgroup. If the order of X is n, then, and here I mean a finite n, then x to the a is h, if and only if g sub d of a and n is 1. So the number of generating elements of H, which is isomorphic in this case to Zn, is the Euler phi n. Remember, this is the function that the number theoretic function we had earlier that counts the number of integers between 1 and n that are relatively prime. I'll leave the proof of this to you all. It's mostly the notes, but let me give you an example that illustrates this. Let's look at Z12. Well, start down here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, and here, my notation is additive instead of cyclic. The generators of this additively is everything that's relatively prime to 12. So 1 will generate it. 1 will always generate any Zn. We discussed that earlier. 5, 7, and 11. Every other one of these single elements generates a subgroup, cyclic subgroup of smaller order. For example, this one generates 2, 4, 6, 8, 10, 0, and then it goes back through. This generates 3, 6, 9, 0. So they all generate smaller subgroups. Only those 4 that are relatively prime generate full subgroup. 0, 3, 2, 8. This is a very simple theorem about cyclic groups. Suppose that I have a cyclic group. This actually has a lot of applications, as a matter of fact. Number one, any subgroup is cyclic. And number two, if it's cyclic of finite order, if the order of G equals n, then there exists a unique subgroup. And of course, the subgroup will necessarily be cyclic of order m for all m that divides G. So for example, if the order of G is 12, like here, take every divisor of 12, 1, there's a subgroup cyclic of order 1, and it would just 0 itself. 12, the whole thing. 6, 0 bar, 6 bar. 3, 4 bar, 8 bar, 0 bar. So any divisor, there's one and only one subgroup of that particular order. I will leave the second part. It's in the notes as well to discover this one. This one's a fun one to play with. If you really want to learn how to deal with cyclic groups, this is a good one to play with. Number one is a nice application of Euclidean algorithm. And suppose H is a subgroup of G. We need to show that H is cyclic. If H is equal to the identity, then done. Because of course the identity is cyclic. If not, there exists smallest k in the natural numbers such that x to the k is in a. You might say, what if they're all negative? But remember, if k is negative, its inverse has to be in there, and so that would be a positive exponent. I claim that h is generated by x to the k, where this is the smallest exponent. I'll prove this quickly. Notice that that's certainly true because x to the k is nh, so whatever subgroup it generates must be nh. Now for the other containment, if x to the a is in h, then because of course any element in h is in G, so it's got to be a power of x, then write A is equal to QK plus R, where R is between 0 and K. There's that Euclidean algorithm all over again. And here's how it's going to help us out. X to the A is equal to X to the QK plus R, which is X to the K, the Q power of X to the R, which is X to the R. Right? Since, and notice that of course this is in H because X to the A is in H, so and it equals X to the R. By minimality of R, I'm sorry, minimality of K, R must be 0. It can't be positive because the K was the smallest exponent that was in there. Therefore, A equals QK, and so X to the A is X to the K to the Q, which is in the ideal term of X. That shows both containments, and so we have our desired result. Okay. I think this is a good place to finish up. I hope you all out there are staying safe, and we will see you when we return.